Hello students, today we discuss one more method to solve non-linear partial differential equation in order 1 if given equation is in some particular form. Here the form contains the variable x, y, p and q only, means variable z is absent here, and at the same time given equation can be separated into the terms of x, p and y and q separately. That is, we can separate x and p into left hand part and we can separate y and q into right hand part. Then we can apply the following procedure. If given equation f, which is x, y, p and q, we separate it into two function f1 and f2. f1 is function of x and p, f2 is a function of y and q, and they both are equal. Now we use Charpit auxiliary equation, which is dp upon del f upon del x plus p del f upon del z equals to dq upon del f upon del y plus q del f upon del z equals to dz upon minus p del f upon del p minus q del f upon del q equals to dx upon minus del f upon del p equals to dy upon minus del f upon del q. From this equation, we calculate partial order derivative of f with respect to x, y, z, p and q. As z is absent here, that's why del f upon del z is always 0. So this term will be 0 always. This is also 0. So these both are 0. Now we calculate partial order derivative of f with respect to x. So x is present here in f1 only. In f2 x is absent. So del f upon del x will be equals to del f1 upon del x. So in place of del f upon del x, we can write del f1 upon del x. When we differentiate it with respect to y, del f upon del y, as y is present in f2 only, y is not in f1, so del f1 upon del y is 0, and del f2 upon del y we can have some value, and this is so del f upon del y is equals to minus del f2 upon del y. So in place of del f upon del y, we write minus del f2 upon del y. Similarly, we can calculate del f upon del p, which is equals to del f1 upon del p, because p is absent in f2, and del f upon del q is equals to minus del f2 upon del q. Putting these value in this equation, we get this form of Charpit auxiliary equation. Now from here we are to get a relation between p and q, or at least one of p and q. So we use first fraction and fourth fraction. Using these two fractions, we get a relation like dp upon del f upon del x, which is first fraction, and fourth one is dx upon minus del f1 upon del p. When we simplify it, we can rewrite it as del f1 upon del x, shifting this into right hand part and shifting it into left hand part, plus del f1 upon del p dp equals to 0, taking both into one side and right hand side equals to 0. This is what we know. f1 is function of x and p, so it represents total derivative of f1, that is df1. df1 equals to del f1 upon del x into dx plus del f1 upon del p into dp, and which is equals to 0. So df1 equals to 0. Now when df1 equals to 0, it means when we integrate it, we get f1 is equals to a, where a is some arbitrary constant, and from here f1 is equals to f2. So if f1 is equals to a, f2 must be equals to a. So f1 equals to f2 equals to a, some arbitrary constant. So f1 function of xp equals to f2 function of y and q. They both are equals to some arbitrary constant represented by a. Now from f1 equals to a, from the equation f1 xp equals to a, we will find the value of p. Say this is equals to some capital F1, which is function of x and a, and from the term f2 yp yq equals to a, second equation f2yq equals to a. From here we will find the value of q, which is equals to capital F2 and F2 is function of y and a. Now we will put the value of p and q in equation dz is equals to p dx plus q dy and integrate it, which gives us a complete solution of given problem. So let's revise its procedure. Very first we are to look that in given equation z must be absent, and then x we separate the term of xp and yq in such a way f1 xp is equals to f2 yq, and now we equate this equation equals to a, that is f1 xp equals to f2 yq equals to a. Now from here we will find the value of p and value of q and put these value into equation dz is equals to p dx plus q dy, which gives us a complete solution. Now let's try some problem. We have x into 1 plus y p is equals to y 1 plus x q. Here z is absent. Now we are to separate the terms of x and p in one side and y and q into in another side. So we divide this whole equation with 1 plus x and 1 plus y. So here in left hand side we get x upon 1 plus xp, and in right hand side we get y upon 1 plus y. When we divide the whole equation with 1 plus x 1 plus y, in left hand part we have the terms of x and p only, and in right hand part we have the terms of y and q only. Now we will equate this equals to some arbitrary constant a. So taking f1 xp is equals to a, we get the value of p, and p becomes a 1 plus x upon x. Similarly, when we equate second term y upon 1 plus y into q, which is f2, taking equals to a, we get y upon 1 plus y q equals to a, implies q is equals to a1 plus y upon y. Now we have the value of p and q. Now we will put these value in the equation dz is equals to p dx plus q dy. Now after putting we get dz is equals to a 1 plus x upon x dx plus a 1 plus y upon y dy. Now we will separate this term, we get a upon x dx, a dx, a upon y dy, and fourth term is a dy. Now we will integrate this equation, we get z is equals to a, here we get ax, it gives ay, it gives a log x, and this gives us a log y. Or we can write it as z is equals to a, taking a outside, x plus y plus log of xy. Using the property of log a plus log b gives us log a plus log ab. So we get log xy plus b, which is an arbitrary constant. Here a and b are arbitrary constant, and this is complete solution of given equation. Let's take another problem. Py plus qx plus pq equals to 0. Here also z is absent, and we are to separate in terms of p and x in one side and q and y into another side. So we divide given equation with pq. We divide given equation with pq, we get 1 upon qy plus 1 upon px plus 1 equals to 0. Taking 1 upon px plus 1 in left hand part and shifting 1 upon qy into right hand part, we get this. So this is equals to f1 and right hand part equals to f2. So f1 is equals to x upon p plus 1, or we can rewrite it as x plus p upon p. From here we will get the value of p by equating it equals to a. When we equating it equals to a, we get x plus p upon p equals to a. It gives us p is equals to x upon a minus 1. When we simplify it by this way, we get p is equals to x upon a minus 1. And from right hand part, equating right hand part equals to a, we get the value of q, which is minus y upon a equals to a, implies q equals to minus y upon a. Now we will put the value of P and Q in dz is equals to P dx plus Q dy. And now after putting the value of P and Q in this equation, we will integrate it, and after integration we get z is equals to 1 upon a minus 1. Integration of x is x square by 2 minus 1 by a. Integration of y with respect to y is y square by 2, and it becomes 2z is equals to x square upon a minus 1 minus y square upon a plus c1, where c1 and a are arbitrary constant. So this is complete solution of given problem. Let's take one more problem. Z square p square plus q square equals to x square plus y square. Here in this equation z is available, x, y, z, p and q all are available. So either we will go for char pit method, or if we want to go for some particular method or especially this method, we are to eliminate z first. To eliminate z from here, we are to use some transformation. So very first we will write p as del z upon del x and q as del z upon del y. So we get this equation in this form. Now we will rewrite z del z, this term z square del z upon del x whole square as z del z upon del x whole square, and second term, which is z square del z upon del y square, we will write it as z del z upon del y whole square equals to x square plus y square. Now if we want to replace z del z with some another variable which gives us del of another z, or say capital Z, so let's take z del z is equals to dz. Z dz is equals to dz. When we integrate it, we get z square by 2 is equals to capital Z. It means if we use this transformation, this becomes del of z. So equation 1 become del z upon del x whole square plus del z upon del y whole square plus x square plus y square. Here z is absent in this equation, z is absent, or we can take del z upon del x as capital P and del z upon del y as capital Q. So it becomes p square plus q square equals to x square plus y square. Now we will separate the terms of x and p into left hand part and putting separate the term of y and q into right hand part, and hence we get f1, which is function of xp, x and p is p square minus x square, and f2, which is function of y and q, is equals to y square minus q square. Taking it is equals to a square. A is arbitrary constant. We will take it as a form in the form of a square. So let's equate it equals to a square. So we get p square minus x square equals to a square, y square minus q square equals to a square. From here we will get the value of p. Here p square is equals to a square plus x square, or p is equals to square root of a square plus x square. Similarly from here y square minus a square equals to a square, we get q square, y square minus q square equals to a square gives q square equals to y square minus a square, or q is equals to square root of y square minus a square. Now we will put the value of p and q in this equation. Dz is equals to p dx plus q dy. We get dz is equals to square root of a square plus x square dx plus square root of y square minus a square dy. Now we will integrate it, and as we know, integration of root of a square plus x square with respect to x is x by 2 square root of a square plus x square plus a square by 2 log of x plus root of a square plus x square. Similarly, integration of square root of y square minus a square with respect to y will be y by 2 square root of y square minus a square minus a square by 2 log y plus square root of y square minus a square, and plus b, which is an arbitrary constant. So capital Z is equals to this one. Now we will replace capital Z with actual Z, which is small z, which is using the relation capital Z is equals to z square by 2. So we get z square is equals to in the form of x, y, a and b. This is complete solution of given problem. Here a and b are arbitrary constant, or here we write b1 which is equals to 2b, as we cancel out 2 from both sides, so here b becomes 2b. So b1 is equals to 2b, which is an arbitrary constant. So that's all about third method to solve non-linear partial differential equation if it is given in some particular form. There are some problem for solving. Thank you.